Welcome. In this video we look at 3.5 derivatives of trig functions. So far we've looked at several kinds of functions that we can take their derivatives of. We've looked at polynomials and rational functions and functions of the type e to the kx. We've seen the product rule and the quotient rule, and we're sort of building up our library of functions that we can take derivatives of. And today we turn our attention to trigonometric functions. So the two basic trig functions are sine and cosine, and I'll ruin the surprise for you. I'll just tell you what their derivatives are. It turns out that the derivative of sine is cosine, and the derivative of cosine is negative sine. Let's look at some graphical evidence for that. So here we have the graph of sine, and I can move my x value right to the center, right to 0, and notice that the tangent line at 0 has a slope of exactly 1. And then as I move it to the right, I get to about pi over 2. The tangent line has a slope of 0, and then right around pi, the tangent line has a slope of negative 1. And if I start graphing out the slopes of sine, the function that I get looks like this. So negative slopes, negative values. Positive slopes on sine, positive values for the derivative. And I can trace it backwards as well. And the orange curve, the derivative that I've just created, is in fact cosine. So the blue curve, the original one, was sine, that goes through the origin. And the orange curve, its derivative, is cosine. So the derivative of sine is cosine. Now let's try the derivative of cosine. There's my cosine being graphed out, and if I trace out the derivative, let's see. So when cosine has negative slope, its derivative has negative values. When cosine has positive slope, its derivative has positive values. There we go. Cosine has negative slopes. Cosine has positive slopes. And so, at the end of this process, I see that my original function in blue was cosine, and its derivative, look at that, it goes through the origin, so it looks a little bit like sine, but it's actually flipped over. It's flipped over the x-axis. So in fact, the orange curve is negative sine of x. All right, going back. So we can use these rules with sines and cosines to compute some basic trig functions. So let's say I want to compute the derivative of sine x plus 8 cosine x. Well, derivative of sine is cosine, derivative of cosine is negative sine, and so we get cosine x minus 8 sine x. How about this? Compute the derivative of sine squared of x. Well, I really think that sine squared. Oh, and by the way, this notation, the square is over the function name. That's really just another way of saying sine of x times sine of x. So the derivative of sine x times sine x. So let's use the product rule. This is, my first factor is u, the second factor is v. And so u prime v, so cosine of x, sine of x. So u prime v, and then plus u v prime. So sine, and then the derivative of sine v prime is going to be cosine. Oh, but look at that. Both of my terms are the same, cosine sine or sine cosine, and so we get, as our solution, 2 sine x cosine x. Now, what about if I continue taking derivatives? So the derivative of sine, if my f is sine, then its derivative is cosine. And the derivative of cosine is negative sine, and let's just keep going. Now, what's the derivative of negative sine? Well, the derivative of sine is cosine, but I'm multiplying times negative 1, so my constant multiple rule says I'll just get negative cosine. And the derivative of negative cosine will be negative times negative sine, and that just brings me back to sine again. So look at this, it's kind of cool. There's this loop that keeps going. I start with sine x, it goes sine, cosine, negative cosine, and then it becomes sine x again, and then the pattern continues. Sine, cosine, negative cosine. What will the 37th derivative of sine b. Can you see what that is before I show it? Well, here's the thinking. My 0th derivative was sine, and my 4th derivative is sine. Every 4th derivative. So I expect that the 36th derivative, 36 is a multiple of 4, the 36th derivative will be sine, which makes the 37th derivative cosine. How about the other trig functions? The derivative of sine is cosine, the derivative of cosine is negative sine. Here's a new one, the derivative of tangent turns out to be secant squared. And for our other 3 trig functions, we have different kinds of identities. Where do these facts come from? Well, all of them can be proven using the quotient rule, and in fact very easily. And the idea is that all of my trig functions are defined in terms of sine and cosine. Well, in fact, sine and cosine, of course, but then tangent is sine over cosine. Secant is really 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tangent. So if I know the derivatives of sine and cosine, then I can use the quotient rule to figure out all the others. So in fact, let's take this one. Let's take tangent, and I'll go through the quotient rule showing how we figure out that the derivative of tangent is really secant squared. Claim: the derivative of tangent is secant squared. So the derivative of tangent is the derivative of sine x over cosine x. And now I need to use the quotient rule. So just off to the side, I remember it's u prime v minus u v prime over v squared. I guess how I remember this is that when I want to take the derivative of a quotient, u is on top, v is on the bottom. The top looks a little bit like the product rule. Let me write the product rule up there. uv equals u prime v plus u v prime. Maybe I should start with the product rule. The way I remember the product rule is that when I begin, I'm very excited to take the derivative. I just can't wait to take the derivative. So when I first run across the u, I take its derivative immediately. But then I remember, oh yeah, now I need to wait, and so the v does not have its derivative taken. And then I add, and I get the same idea in the next term, but with the derivatives switched around. So then v gets its derivative. Notice the product rule, that sum looks a little bit like that difference. The u prime v is the same. So u prime v at the beginning, u prime v at the beginning there, u v prime as the second term. The difference is that in the quotient rule I subtract, whereas in the product rule I'm adding. And then somehow you just have to remember to take v squared on the bottom. I don't know how you remember that. Just remember it. Okay, with all of that said, let's return to this problem. Okay, so u prime v minus u v prime all over that denominator squared, which is cosine squared. Simplify that numerator a little bit. Cosine squared x plus sine squared x over cosine squared x. What is the one trig identity I told you that you had to memorize at the beginning of the semester? Sine squared plus cosine squared equals 1. And look at this. So if I have something like 1 over x squared, right, that's the same as 1 over x being squared, right? So now that becomes 1 over cosine squared. And what is 1 over cosine? Simply secant. So there we go, right? Looking at the beginning, the derivative of tangent is secant squared. Lastly, let's prove that the derivative of sine is cosine. So I've been using this fact for the whole lecture up to this point, but now we actually need to prove it. So this is the foundation upon which everything else stands. In order to prove this, I will need 2 limit facts. The first is that the limit as x goes to 0 of sine of x over x equals 1. I won't prove this, but here's the picture, and hopefully this seems reasonable. The picture, that's the graph of sine of x over x. And look, as x approaches 0, the value of sine of x over x looks like it is approaching 1. The other limit fact that we will need is that the limit as x goes to 0 of cosine x minus 1 over x equals 0. Here's the picture of that, and as my x values approach 0, it looks like those y values are also approaching 0. We will need one last fact, sign addition. It turns out that the sine of x plus h is sine x cosine h plus cosine x sine h. There are many, many, many of these trig identities. Here is just one of them that happens to be useful for us today. Okay, this is the background. This is all that I need now to prove that the derivative of sine is cosine. So here we go. Let f of x be sine of x. Then, by the definition of the derivative, here is my derivative. F prime of x is the limit as h goes to 0 of sine of x plus h minus sine of x over h. What will I do next? Do you see? Now I can use that sine addition identity, and I expand out the sine of x plus h. Now, at this point, I'm going to break this up into a couple fractions. This quantity, I'm going to break apart on its own. It comes down to the right. And all the other parts, those come together down on the left. And I'm factoring out a factor of sine x. Now, at this point, something interesting happens. Notice I'm taking the limit as h goes to 0. So h is the quantity that's changing. But sine of x, then relative to h, that's a constant. So in fact, this sine of x, I can pull out front of the limit by the constant multiple rule. Same thing on the fraction to the right. Look at this. H is changing as it goes to 0, so cosine of x is a constant. I can pull cosine out in front. And I get sine of x times a limit plus cosine of x times a limit. What are those limits? Look at that. Those are the two limits that we saw on the previous slide. Sine of x times 0 plus cosine of x times 1, and that is cosine of x. So there it is. Now, I don't present these proofs to you and expect that you memorize them and spit them back out at me at some point. I will not ask you to prove that the derivative of sine is cosine. But I think it's important for me to demonstrate this because I really want to emphasize that all of these derivative rules that we find, they're shortcuts and they're easy to use, but it's easy to lose sight of the fact that we really proved them, and we proved them based on the definition of the derivative. So it all comes back to understanding how the derivative is defined. Okay, I will stop there. That finishes the lesson on derivatives of trig functions.